So first we're going to talk about descriptive models. This is the majority of what people are doing out there in the real world, kind of implicitly. It's also kind of the most useless thing because for descriptive analyses, there's generally not really a well-posed question. People are usually asking the model to tell them kind of everything there is to know about this entire system, and the model can't really do that. Moreover, if you compare these two different linear regressions, as we saw last time or 2 lectures ago, these two coefficients have different meanings and interpretations. So this coefficient is, what happens to the predictions if I increase x1 and I let x2 do whatever it wants because x2 is not in the model. Whereas this one is what happens if I increase x1 and I leave x2 fixed, and I also somehow leave these terms fixed, which include x1. So this kind of intuitive interpretation of this coefficient in this model is actually not that useful, and it is also completely different than the one in this model. It's not, you can't just say that this coefficient is the association of x1 with y here, because here you're saying, okay, this is the association of x1 with y kind of above and beyond these other associations, which, how do you even make sense of this? And this one is the association of x1 with y, just kind of, period, assuming everything else is allowed to vary with x1, right? If I change x1, x2 might change. I'm fine with that. So these have different meanings, different interpretations. It's not really a good question that you can be asking here. But nonetheless, people do these kinds of analyses, and they generally want, if you ask people, they'll say, oh, I just want a kind of simpler model. I want something that's parsimonious, something that I can kind of explain, rather than something that's unnecessarily complex, right? So people would look at this interaction term or the squared term and say that's unnecessarily complex, because then I can't interpret this coefficient the way that I, would like to, as just holding everything else constant. What happens if x1 increases by itself? Because I have this thing. So I'm just going to say that's complex. I don't like it. Okay. So, but do I need it? Maybe I really do need it. And so there's a kind of trade-off between needing it and this complexity. And what people mean by that is often kind of vague. But let me just show you what is often done in practice. You may see papers that do this. So this is a technique called stepwise regression. And stepwise regression is basically an automatic way of adding or deleting terms from a regression model to get a model that's as simple as possible, but as what it is that you're selecting for is sometimes vague. But in this case, you're trying to get the most variables that are somehow significant in some kind of a adjusted sense. So the reason I'm being vague about this is because I'm just going to tell you that this process doesn't really make a lot of sense generally. I'm showing it to you because this is what people do, so you need to know that it's out there. And so I'm just going to explain what it is that it does, and then we'll critique it a bit. So here's, you can begin, and this is just one version of this. There's other versions that are fairly similar. So say you're starting with a model that just has an intercept. You're going to calculate the p-value for each variable that's not in the model. So you're going to run univariate regressions against all other variables, and then any of those univariate regressions that are significant, you pick the one that has the smallest p-value and you put that variable into the model. And then basically you repeat. So now you have a model with one variable in it. So you look at all the other, if you were to kind of add a single variable, you run the regression with that variable and each of the other ones. And then you see which of each of the other ones has the smallest p-value. And then you keep that one, and then you keep going like that, okay? That's generally the idea. You don't have to be able to do that by hand. Actually, I mean, you should basically never be doing this anyways, but you don't have to be able to do it by hand because R can do it for you. So let me show you what that looks like. So I'm using this drippy little data set called empty cars. It just has a bunch of cars in it. This one is not public health related, sorry. But so we have for each car the miles per gallon that it has, the number of cylinders in the engine, and some other kind of statistics about each car here. And what I would like to do here is, okay, so I'm gonna start with my initial model. So you see in the beginning, I just have the intercept. And then I'm going to say the biggest possible model I could have, the most complex model, is going to be this one, okay, where I have all of the terms, what I'm doing here is I'm trying to regress how many miles per gallon each car has onto all the other variables. And I'm also going to allow interaction terms between any variables and this WT, I think it's the weight of the car, because I think maybe those interactions are important. And I say that's the biggest possible model. Now find me kind of the sweet spot in between there. So I can run this step thing. I say basically add terms until you get to this, or you stop because you're not improving the model at some point. So this is what the output will look like. So you see first, you have the intercept-only model, and it says, okay, if I added each of these are some kind of stats that I get. So RSS, residual sum of squares, is the same as mean squared error. So, here's the mean squared error when I added weight. So that's a very important predictor, it seems, at least in the univariate sense. And so it says, okay, I added weight to this model. And now it says, if I add cylinder to this model, this is the resulting MSE. If I add HP, this is the resulting MSE. And there's some other statistics. So it decided to add cylinder. Here it's looking at this. Since it's already added both of these, it can now, this is just the way the algorithm works. Once you've added both two variables, it can now choose to consider the interaction. That's ad hoc. There's no reason why you can't have started with considering all possible interactions and not the main terms. But for whatever reason, people think, well, you can't have an interaction term if you don't first have the main term in there. But there's really no reason for that. It's just convention. So here now it's considering this interaction, and it says, okay, that interaction is actually more important than any of these other variables. So it's going to add that in. Now it says, okay, the qsec is important, so it adds qsec in, at which point it can start considering this interaction, which it turns out is not that important by these metrics. It decides to add gear. Or actually here it decides to stop, because it basically it says, okay, my improvement is nothing from the previous step. If I add nothing, oh yeah, so here it says none, right? If I don't add anything, I'm not substantially improved. The difference between adding the best thing and adding nothing is not that different. So I'm just going to stop because now I'm good enough. So it says, here's your final model. It's this. This is the kind of parsimonious model that we ended up with. So that's basically stepwise regression. Okay. There's problems with that. The problem number one is that it's basically impossible to interpret whatever final model you get, right? Because for one, these already we talked about, these coefficients have different descriptive meanings and interpretations. So if you're kind of coming to the data with a question already, then it doesn't really make sense to look at the model that gets generated by this thing and then try to interpret those coefficients. Maybe the thing that you're interested in is not even being addressed by the coefficients that are returned. And also, how do you interpret? You don't know before you do this process which of these you're going to get, right? Because it depends on the data. And for different data sets, you may get different models out, right? Even if it's drawn from the same data generating process, you can do this. You can subsample the car's data set and do this thing, and you might get a different model than if you take a different subsample. So the structure of the model itself is random now. So, how do you interpret this thing when you might have actually gotten that thing? And then, of course, do the selection criteria. So I didn't really tell you what it's doing. In this example, it's based on these p-values. R, it seems like it's basing it on some kind of mixture of, mean squared error, degrees of freedom, which is basically how many coefficients are you adding to this, and this thing called AIC, which we'll actually talk about in a little bit. So how you decide on whether you're going to keep a variable or discard a variable or whatnot will affect the kinds of models that you get, of course. And the question is, do those selection criteria, whatever you're using, does that actually reflect what you care about scientifically? Any kind of question that you have. And often the case is no. So what are we doing here? The second problem, which is a bit more subtle, I think, is that if you do this, your confidence intervals, basically all of your inference is totally whack. It doesn't work anymore. So let me show you what I mean by that. Okay, so let's try this in R. Let me show you first this data generating process, what this looks like. So if I generate, let's say, just 5 samples from this, I get x1, 2x, 10, which is not being shown here. So I have 10 random variables in this data generating process. They're all normals. They all have mean 0, standard deviation 1. So they're all the same. This code just makes it so that I can generate, if I wanted to do, 100 of these, I could say p, or let's say p equals 3, or p equals 3. Yeah. So now I only have 3 of them. Okay. So that's all this code is doing. It's not important to understand it. Feel free to read and take what you want from it. But that's all I'm doing. I have 100 observations of 10 standard normal random variables. And I'm going to set up this estimator. What the estimator is doing is that it's going to estimate I'll just show you. We're estimating the mean of each of these and the standard error of that mean. We're looking at the p-value of all of those. So which of these means is most significantly non-zero? And then we're returning just the one that is most significant. So we're kind of looking at all of these random variables. Let's say we don't know, right? We don't know that they are mean 0. We think some of these may have higher means than others, right? So an example of this, maybe this is like the levels of different biomarkers in the blood of different people, and we want to know which of these biomarkers is most elevated or is most significantly different from 0. Okay, which of these has abnormal levels in this sample in this population that we're studying. So something that you could do is you might test all of the biomarkers and say, oh, this one has the most abnormal levels. Let's report that one. So that's essentially what this is doing. So if I generate some data, let's say DGP 100, and then I put it into this estimator. Okay, what we get here out is X1. So in this data set, X1 had the largest, had the most significantly non-zero sample mean, and it's not super significant, but it's a p-value of 0.14, and we have our estimate being 0.15, right? So we would you might conclude from this, okay, this is not totally inconsistent with the null hypothesis that X1 has mean 0, but it's kind of evidence perhaps tending towards the fact that X1 has a non-zero mean. Let's say I do it again. Okay, now I get a different answer, and I get a tiny p-value, right? So in this analysis, just with a different data set, now I'm very confident that X3 has a non-zero mean. We know that it doesn't, right? But here it shows that it does. And here's another case. Here we're, again, maybe not by the 0.05 threshold, but we're pretty confident that X6 has a non-zero mean. Here we go. Okay, that one is a little less confident. This one is, again, almost statistically significant at the 0.05 level. X1 has a non-zero mean. But what you see is happening is that each time I run this, we're very confident that one of these variables has a non-zero mean, or at least fairly confident. And so let's just run this 1,000 times. Here we have 50 random variables that we're including in the DGP. Okay, and now I'm going to show you the distribution of the estimates from this estimator. So these are the sample means of the variable with the most significantly non-zero sample mean. Does this look normal to you? Does this look asymptotically normal and unbiased? Maybe it's unbiased, right? Because kind of on average, we are getting 0, but certainly it is not normal, right? Because what's happening, and we can also see, well, I'll show you this later, but what's happening is that because in the model selection process, we are picking the variable that has the most significant, statistically significant difference from 0. We are basically always getting these more extreme answers, right? And since it's just significance, it could be positive, it could be negative. That's why it ends up looking like this. And then if we say, okay, well, if we look at the p-values, or let's just look at the standard errors, right? The standard errors that we're estimating in each for here, right? This is just basically the standard deviation of X1 divided by square root n, right? That's the standard error for the mean. And then the p-value is based on that, right? So that's the right formula for the standard error of the variance, the standard error of the sample mean, right? But if we look at how does the standard error that we're estimating, the average of that, how does that compare to the actual standard error of this distribution? So this is the actual standard deviation of this distribution. And this is the standard errors that we're estimating. This is way smaller, right? So we're basically much more confident than we should be. This is totally wrong. But how can that be if we're calculating this using the right formula and the assumptions of that formula are satisfied? So here we'll discuss that, right? So the idea is that we're assuming that this is the picture. We're assuming that we put our data in, and really it's, in that example, we're doing x1, x2, x3, whatever. But it's the same message if we're doing a kind of stepwise model selection or whatever. Basically, you're considering multiple different hypotheses. Is it x1? Is it x2? What am I going to add in the model? So our data is going into the estimator, and we're getting the estimate. And in our example, the estimate was the mean of one of these x1 or x2, right? And in the model selection example, this is, or in the forward stepwise regression, this might be a coefficient or something like that, okay? So this is what we think is happening. And so we can base inference based on this estimator. We find a formula for the asymptotic error, blah, 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 all the same kind of stuff that we've done before. And then we can construct our confidence interval. Great. But that's not what's actually happening. What's actually happening is this, right? We first are taking our data and putting it into this algorithm, which is doing some kind of model selection, choosing what coefficients to include, or choosing whether we're going to look at x1 or x2 or whatever. And then that's going to say, oh, the final estimator is look at x1 and then take the sample mean of x1, right? But we didn't know before we looked at the data that we were going to look at x1. Before we looked at the data, it could have been x2, it could have been x4, we didn't know. We didn't know that the linear regression was going to have beta 1, beta 2. It might have just had beta 1. So we didn't know before we looked at the data what was going to be in this box. And so this is the actual estimator. It's everything that's going on in here, right? The estimator is what is the process of taking the data and transforming it into a number. And if you think what's going on is just what's in this little box, you're ignoring that this stuff is happening out here. And so your formula for variance, or whatever it is that you're basing the properties of this estimate on, if you're basing it on the behavior of this final estimator, you're wrong. Because this actually depends on the behavior of all of this stuff together. And so that formula for asymptotic standard error that is based on this what's happening in this box is not accurate, because it doesn't take into account the variability that comes from doing the model selection itself, right? So model selection bias, this is, by the way, also the same issue as multiple testing or multiple hypothesis testing, if you've heard of that, especially in the context of like GWAS studies, where you're testing like thousands and thousands of genes to see which gene is most significantly associated with a particular disease or expression of something. All this is the same problem, which is that you did a lot of stuff. You tested 1,000, 10,000 different genes, but then at the end you pretended you just tested one, which is not what you did, right? So you have to take into account what you actually did in order to understand the properties of that estimator, the bias and the variance, and you can't just ignore it. And when you do forward selection in R, if you just get the thing at the end and you look at the confidence intervals and things like that, that's not actually reflective of what happened. So here's a nice little comic, XKCD, you may have seen, about multiple testing, just to put it in a very concrete way, right? So you have this situation, oh, maybe jelly beans cause acne, let's investigate, right? And okay, they do the analysis, basically collect some sample, look at who's eating jelly beans, who has acne, and then see if there's some association, maybe run a regression. P is not significant, so no link. Oh, but maybe it's only a certain color. Okay, let's go. All right, so just for purple jelly beans, there's no association. For brown jelly beans, there's no association. For pink, for blue, for teal, for salmon, red, turquoise, magenta, yellow, no association. Gray, tan, cyan, no association. Green, oh my god, actually a significant p-value, less than 0.05. Okay, what about mauve? No. Beige, lilac, black, jelly beans, peach, orange, none of these have significant associations. But this green one, right? Put it in the news, right? Green jelly beans cause acne, right? And in fact, there's 95% confidence of this. That's how people would report this. There's only a 5% chance of coincidence. That's what the p-value means, right? The p-value less than 0.05 means that out of 20 findings, out of 20 results that had a p-value less than 0.05, only one of them is actually going to be a false discovery. But what did you do? You just ran 20 experiments and you got one discovery, right? So it's actually very likely that that one is a false discovery. So this p-value, basically all kinds of inferences that are based on this multiple testing or model selection, they all need to be adjusted to account for the fact that you did a lot of stuff, right? You went digging to try to find something, and you're always going to find something if you go digging, but it's probably fake. So what can you do? Well, there's all sorts of crazy fancy stuff. If you just Google like post-selection inference, there's a lot of elaborate math that you can do for very special cases. Not worth getting into. Here's an easy thing you can do. Just split up your data. Okay, split up your data. You take some portion of the data, maybe let's say 40%, and you use that 40% to do the model selection process. So, kind of guessing what terms should go into the model, what variables should be looking at, if there's interactions that you want to include. That's done, right? Then basically throw this away and never look at that sample again. Go to another sample. Let's call this the model selection sample, which you just used to pick what terms to include, basically. But then once it picks it, you don't look at the coefficients, you don't look at the confidence intervals, you just ignore all of that. You just have it tell you what terms you should include. Then you should go down here, you use your estimation sample, which is maybe 60% of your data, and then you fit the model with these terms, and you're going to get a different coefficients than you got up here, right? Because it's a different data set. You fit that, and then you can report that. Why is this better? Well, because from the perspective of this estimator, the estimator was already chosen, right, before we looked at this data. So it was a priori selected. And so another way of you don't have to do this with one data set that you split. Let's say you're running an experiment. You've already run like 20 experiments in the past in your lab. So you have all this old data lying around. You can use that old data to do model selection before you run your experiment. Decide what kind of terms you're going to include. Then you run your experiment, and then you apply that estimator, right? So it's basically like if you're doing this, you've decided on the estimator that you're going to use before you look at the data. And so the choice of what these data do not impact what goes in this estimator. And so the asymptotic properties or any kind of inference that you're going to do about this estimate are really reflected by the kind of properties of this estimator based on the randomness of this data alone and not on the randomness of this data. All right, so which of these should set off your red flags for model selection bias? So let's say you're reading a paper, right? And or 4 different papers, and those 4 different papers have these different sentences in them, and you come across them. I just want you to tell me, if you're reading this, which of them should make you kind of be like, ooh, cringe, right? That's the question. So first one, we tested 1,000 genes and found that 50 has significant association with the disease. P-values are reported here. Definitely cringe, okay? Out of 1,000 genes, if you're looking at a 0.05 significant p-value level, then you would expect that 50 have significant findings, even if all of them have no association, right? So if then you're reporting those p-values, those are meaningless. Okay. After fitting our model, we removed variables without significant associations. The final estimates are so same reason. If they looked at the data and then used that data to decide what model was being fit, that's very similar to this multiple hypothesis testing. You're doing multiple models, you're testing these multiple different models, and then you're picking the one that has the highest significance. For any data set, another way to think about this is that some model is going to have some significant something, right? And so if you're picking the one that has some significant something, you're not accounting for the fact that, randomly when nothing is happening, some model is going to pick up on something. So this is garbage. Based on repeated testing with prior data, we settled on these 4 terms. We then refit the chosen model on our new data. This is great. Nothing wrong with that, because they used a different data set to do the model selection than they did to do the estimation. So it's perfectly reasonable to look at, read a bunch of papers, for example, and say, hey, it looks like from all these papers, people seem to think that there's a nonlinear association or the nonlinear relationship between, age and risk of death or something like that. And so I'm going to go collect data and run a different kind of analysis, but in that analysis, I'm going to include a nonlinear term in my regression because of what I read in these papers, because that was not based on the data I'm going to collect. All right, this one, by testing many models, we found that including these two interactions significantly increased the R squared. The final estimates are, so this one is very similar to this one. It's now, they've just changed what they're using to do the selection. So instead of doing the selection based on the p-values of the individual variables, they're doing the selection based on what is increasing the overall R squared, but still not accounting for the fact that you did a lot of stuff, right, to get to these final estimates. All right, so model selection for descriptive inference. We've been talking about the inference part of it here, which is, definitely shady. You can correct it by doing the sample splitting, but at the end of the day, it's just hard to interpret this because you don't have a real question usually, right? And so it's not that useful overall, even if you can fix this problem here, I think.